So let's walk through the code that uses stability diffusion pipeline to generate an image from the prompt, from the text prompt. So here I'm using a Google Colab Pro. I want to make sure first of all we are setting up a GPU environment. So I'm going to select a runtime and I'm making sure I have selected at least one of the GPU. In this particular case I'm using an T4 GPU, but you could use any other GPU here. So first thing we need to do is we need to install the several libraries that we'll be using in this particular lecture. So we definitely need a PyTorch and diffusers. Diffusers are basically the Hugging Face versions of the stability diffusion models that we're going to try in this particular examples. And then definitely we use transformers library and SciPy and FTFY library to for text manipulation, and we are going to use accelerate library to speed up the image generation. Then the diffusers, we are going to load up the stability diffusion pipeline. So let's first install all the packages. Since I have installed most of the packages, it is just saying requirements already satisfied. Then I'm going to import the diffusers library from the stable diffusion pipeline and of course the PyTorch. Okay, the easiest way to generate a functional code that generates text from image is basically using a pipe component in stable diffusion pipeline. A pipe component basically it's a default pipeline that generates image from the text. It's already has pre-assigned weights and parameters defined, so that you don't have to worry about configuring each and every parameters, and you can get started very easily. But on the flip side, this doesn't allow you a lot of flexibility. Like if you want to change certain components in the stable diffusion pipelines, you cannot do that very easily. So we will cover both ways, how it makes it easy, things easy using a pipe, and then we will also write a custom inference pipeline by loading individual components. So let's start with a simple pipe components. We are going to load a simple pipe component, and we are saying, hey, load a pre-trained version of stability diffusion 2.1, and then we are going to load float 16, which is a half precision tensors to speed up the pipeline. So let's run the pipeline. So it's loading all the pipeline components which are needed. Then let's convert all of our pipe to GPU. Okay, now let's at this point we are ready to generate the image from a prompt. So our first prompt is a photo of a horse, and let's see, we are just going to pass that prompt to the pipe. The pipe can generate several images, but we are going to just show the first image. So there you go. You see the image of a horse that model is generated just based on the text prompt. Right. Now the model has some additional parameters like guidance scale, as we learned, and number of inference step. As we learned in the past, the guidance scale determines how much freedom the model should have. Like the higher the value of this particular value, it will be closer to the prompt. Lower the value, it will be moving away from the prompt. Number of inference step determines how many times it should work on removing the noise from the image during the inference step. And generate is just a random seed that decides whether the model should be generating same images as generated in the previous path. So let's try with the higher value of guidance scale and see what happens. And this time we're generating the photo of a lizard. The higher value of the classifier guidance scale indicates that the image should be very close to the prompt that you have. And this is the image that it generates. And let's try with the lower value and see what happens. In this particular case, the model should have more freedom to move away from the text prompt, and it can use its own creativity to generate the photo of a lizard, which may not be realistic. It's just using its own creativity. So as you can see, the model is using their own creativity This doesn't look like a real lizard, but the model is using our own creativity. So this is how you can play with the guidance scale parameter. So far you have been displaying one image, but you could also display an image into a grid. So let's write a small utility function called image grid that takes a set of images as the input and displays them into rows and columns specified by this function. So it's a simple function that just creates a grid and outputs the images into this grid. Okay. So let's see, we want to generate the 3 images in this particular case. I want to, and the prompt in this particular is a photo of a car racing. So in this particular case, I should get a 3 images displayed nice in the grid. Alright, there you go. You saw 3 images of a car racing in the car. So now let's look into how we can customize the inference by configuring the individual components inside the diffusion process, and that way we have more flexibility, right? So in this particular case, we are going to get a reference to the individual components of a diffusion model. As we talked about previously, the clip model is responsible for generating embedding from the text. Then VAE has this autoencoder that can generate latents from image and image from the latents. Basically, they are responsible for generating a lower dimensional representation of the input image, and then it feeds into the UNet model, which can operate only on latents, and it can do operation at a really faster rate. And in the UNet, we are going to use a UNet 2D conditional model. As you know, UNet is responsible for predicting a noise from the image, and this noise can be subtracted from the image to get a more cleaner image. And for noise scheduler, which basically adds a different amount of noise at each time interval, we are going to use LMS discrete scheduler. And then of course from the diffusers, we are going to use some utility that can convert PyTorch tensors to PIL, and then we can display those images. Okay, so here we load those various components. We load the VAE, we are going to use the stability diffusion pipeline. We are going to use a tokenizer, which basically converts text into numbers, basically the index of that words inside the vocabulary that the tokenizer gives us. And the text encoder is the one that takes tokens as the input and generates the word embeddings for that particular prompt. Okay, so UNet, then we get a reference to the UNet. Again, UNet is also from the stability diffusion pipeline, but you could also vary it, right? You could also use runway MLs UNet. You could play with any different versions, not necessarily from stability diffusion. It could be from any other version of the model component that you can load and play with this. And then we configure our noise scheduler with these parameters, when it should start, when it should wane, and how it should scale the noise, and how much number of training steps it should use, right? Then we convert all of these components to GPU, and now we can start configuring our prompt. So we are saying we have a prompt entry is a photo of an astronaut riding a camel on Saturn. This is the size of the image that we want to generate, 512 by 512. We want to run at least 50 steps inside the model. We want to use a 7.5 as a classifier guidance scale. Then we use a generator, and we use a batch size of 1 because there is one image. Then we start loading the text input, which basically takes in the prompt as input, and then it can returns a PyTorch tensors, and that has the tokenized. The first thing is it tokenizes the input, right? It converts into tokens, and then tokens are converted into embeddings by using this text encoder. So at the end of the day, we have text embedding. Now these text embeddings basically are conditional inputs. As you saw previously, a UNet model takes 2 inputs. One is the conditional input, which is our prompt embeddings, and the other one is unconditional input, which are basically has affinity to noise, right? It is basically empty string, and then we combine conditional input and unconditional input, and we give appropriate weight using the classifier free guidance, as you will see later in the code how you combine that, but at this point it is suffice to say that we need both conditional inputs, which is here, unconditional input, and then we concatenate both of them to generate the text embeddings. So finally the text embedding that we're going to feed in, it has unconditional input as well as conditional input together. Okay, then we generate, so diffusion model takes conditional inputs, unconditional inputs, and we also need to feed in the noise. So we just generate the noise based on the configuration like batch channels, the configuration, the batch size, the number of channels, and height and width. We are going to scale down the image before we generate the, we are going to scale down this noise by a factor of 8. That our input image was 512 by 512, but we are going to reduce the noise size by a factor of 8 before feeding in. Then the latents also we are going to feed into the GPU by using this. Okay, we need to run all of the steps again. Okay, so I'm going to load this, all these components. Okay. Okay, this time it has gone through. So it has loaded all this unit models also onto the GPU. Okay. Okay. So now actually we are going to run through the denoising pipeline, where basically what we do is we first convert unit into GPU. Then for a specified number of steps in GPU scheduler, what we do is first we duplicate our noise input to match conditional as well as unconditional input, and then we scale by a certain factor to be used in the scheduler. Then of course we move both of them to GPU device, and then when the model is running, we are running in the inference mode, so we don't have to calculate the gradients. So we are going to say do not compute any gradients. We are going to feed the noise as an input to this unit model. Then the text embeddings, which is now consisting of both unconditional and conditional inputs. Then the time steps as another input, right? And then we create the sample which gives me the unit generate. As you saw earlier, unit should generate a noise which is in the image, right? Then the noise we are going to chunk it into two, whether it is from unconditional inputs and conditional inputs, and then we are going to scale it by a factor which is in the CFG. This is what we saw earlier, right? Whether the model should have freedom to use its own creativity, or the model should follow strictly the conditional inputs, that is decided by this guidance factor. So we basically, based on the guidance factor specified by the user, we can control how much we should take from the conditional input as well as unconditional input. And then this one, noise predicted, is used, again we compute the gradients from that, and we use that as an input for the next step for the model to figure out. So in the process, we hope that the model is able to generate the image of a better quality at every time step. So after 50 or 100, whatever time steps has been configured for, we really generate the high quality model image. So the unit model generates a latency as an output, so we need to convert that back to an image. So first we need to scale back these latents, because our noise scheduler, as we saw here, it has scaled down our inputs. So we need to scale back our latents, and then we are going to decode those latents into the image, and then we will print the image. So when we print the image, this is the image that we see, where an astronaut is riding a camel on the Saturn. That you can see a Saturn thing here, a camel and astronaut. So this is how we can write our custom inference pipeline, and you can play with a lot of different parameters inside each component. You can also change these components that we have used. So in this particular case, I am using all the different components from the stability diffusion, but you could also use different implementation like runway ML or any other models which are available in the Hugging Face.